Very good. Well, thank you.
So thank you very much for the introduction. I'm a postdoc with Sigurd Skogestad, and since this is the last talk in this session and a lot of you are tired like I am, I put the essence of my talk on this slide. So you see it right away. So if you remember this, I'm happy. So take a close look at the equation before I continue for those who want to listen to some more. Okay, so the outline of the rest of my talk. After a short introduction, I'm going to talk about controlled variables for parallel heat exchanger networks. I'm going to show some examples and a case study. And since everybody's talking about economic eMPC and economic things, I'm going to also do an economic extension of my method. And then I'm finishing my talk with the conclusions. Good. So as a motivation, we look at this crude oil heat exchanger. Can I point? This crude oil heat exchanger unit where at the Mongstad refinery in Norway, where a coal feed is coming in and it is split up into several branches which are heated, and then the heated stream is collected again and goes into the pre-flash column and then the manufacturator and then leaves the system. Now the idea is here, or the challenge is to distribute the feed stream between these lines in such a way that most of the heat of the streams that go out is recovered. Because if we do that, we don't need to heat so much here, and that saves a lot of energy. And in this case, actually, this was the bottleneck of the process in this refinery. So that had a huge economic impact. If we look at it, yeah, it had such a big economic impact that they installed the MPC-based real-time optimization on it. If we look at it more conceptually, again, we have this cold feed. Can I have a pointer on this one?
Yeah, I think that's it.
Here it is. Okay. So you have a cold feed coming in, and it's heated, and then it's split into branches, which are heated by hot streams, and then it goes into the fired heater, and we want to maximize the end temperature here. So adjusting this split ratio such that the end temperature is maximized is not trivial, because the split depends on the temperatures of the hot streams and the flow rates, and also the heat capacity, the heat transfer properties if we have fouling in the heat exchanger. And to optimize this, there are two different approaches. So one is the online optimization approach, which is very popular, especially at conferences. And so we have an optimizing controller here, which takes the states or estimates of the states, flows, and heat transfer estimates of all these parameters, and puts them into a model and then optimizes them online iteratively, and then comes up with the optimal input, which is then injected into the process. If the disturbance changes, then this is just done over and over again. So this can bring you very close to optimality if you put the effort into it and make a good model. Now, the other approach that I'm going to focus on today is an offline optimization approach. So here we say, okay, we take some measurements which are easy to obtain, for example, flow measurements, or temperature measurements. Flow measurements are not as easy as temperature measurement. And then we design some function C of these measurements that if we just control this function C to 0 or to some set point, the input that will be generated by simple controllers will also give close to optimal operation. Of course, this is really dependent on what kind of function we find here. And if we do a good job finding this function, then we call it self-optimizing control. And this has been defined by my advisor Sigurd. He says that it is if we can achieve an acceptable loss from optimality with constant set point values for the controlled variables. So I'm going now to focus on how we can find these variables for parallel systems, and especially this heat exchanger system that I showed you. So typically, if we have a situation like up here, for this heat exchanger network, we have an unconstrained optimum. And in this case, the optimality condition says the gradient must be 0. Equivalently, we can also write this optimality condition in such a way where we say the marginal costs must be equal. So that means that a change in the flow rate on the first branch must have the same effect on the end temperature as a change on the flow in the second branch. So if that's the case, then it's balanced and we're optimal. And so the ideal self-optimizing or controlled variable would be then to say, well, let's just control the difference between these for the two branches here to 0. But it's not as easy because these functions here depend on feed temperatures, on heat capacities, on flow rates, and lots of parameters that are difficult to estimate. So instead, we want to approximate them by simple functions of temperatures. And then we came up with something called Jäschke temperatures. The name was actually proposed by Sigurd. He said, we need a good name for it. And then he said, we'll call it this. Okay, so it might be a bit embarrassing since I'm presenting it, but it's not my fault. So okay, so these Jäschke temperatures are approximations of these marginal costs. And then, obviously, the controlled variable is then to just take the difference of the Jäschke temperatures and control them to 0, or to make the Jäschke temperatures on all branches 0. So now, how do these Jäschke temperatures look like? And now we're getting back to the first slide, if someone with the formula on the first slide. So these Jäschke temperatures are only functions of temperature measurement. So for the first line, the Jäschke temperature is calculated as the difference between the outlet temperature from the heat exchanger and the inlet temperature. So this is the difference. We square that, and then we divide it by the difference between the hot inlet temperature and the feed temperature. So we do that here, and then we just write it short with this delta. So this delta means that we shift the reference temperature from 0 Kelvin or 0 centigrade to the T0. Okay? And so these are the Jäschke temperatures for a system where we have one heat exchanger per branch. And then the optimal control variable, I will show you on the first slide already, is this. Yeah, so now you might say, okay, well, sometimes you have more than one heat exchanger on a line. So we thought that too, and then we found generalization of this formula, which is like the Jäschke temperature for a line with n heat exchangers is just the sum of some contributions for each heat exchanger, and these contributions are calculated iteratively. So and again, just take into account the temperatures of the hot streams and the outlet temperatures together with the feed. So these are all the measurements that you need. You don't need any heat transfer coefficients or heat capacities, or these variables. So if we have two heat exchangers on a line, for example, the Jäschke temperature will look like this. So we have the one for the first one, which looks exactly the same as if we just have one heat exchanger, and then we have the term for the second one, which takes in basically a correction term for that takes into account that there was a heat exchanger before that. Okay, so some more details. These Jäschke temperatures, they maximize the heat transfer under varying flow rates and heat transfer properties and temperatures, and they're the exact solution if you assume you have the arithmetic mean temperature. That's how we got. So under the assumption of the arithmetic mean temperature, you can derive these simple formulas. I could show that that these formulas are true for the case from 1 to 3 heat exchangers, and then for more I conjecture it. So if any one of you wants to put to show me, then you can do that. But I conjecture that it's valid for more, and numerical results show that too, and it's this structure that's repeated. If you have the logarithmic mean temperature difference, then these Jäschke temperatures become approximations of the marginal costs. They're not exact anymore, but for systems which are well designed in the sense that you have similar heat capacities on the flow, on the hot flow and on the cold flow, you will get good results. Okay, so I got some simulation examples to convince you. So here we have like the simple system with a control variable. On this axis I've got the temperature, which I want to maximize. On this axis I've got the split. So here everything goes to the second branch, here everything goes to the first branch. And now at the maximum here, we see that this dotted line, this dashed line, this is the control variable. So it is 0, very close to the optimum. The true optimum is this here. We don't hit the optimum exactly. Why? Because this heat exchanger network was being simulated with the logarithmic mean temperature, and these Jäschke temperatures are defined using the arithmetic mean temperatures. So that's why the split is not exactly the same, but if you look at it in terms of the objective function value that you want to maximize, you get very, very similar values. And I just compared it to another case that's often done, where you say, okay, you just do isothermal mixing, you make the temperature here equal here, and if you do that, you get some loss. So this is clearly better, and we didn't need any optimization. That might be bad news for some people, but yeah, it's simpler. If we have two heat exchangers, then we get this control variable. This part here corresponds to the second heat exchanger, and this here to the first branch. And so here again, we see that the control variable is 0, very close to the optimum. It is not again the true optimum, but that's because we don't have, because of the logarithmic mean temperature difference. But in terms of the cost function, again, so the optimized one and the equal Jäschke temperature one is very, very close. Again, we have some loss with the isothermal mixing. Good, so let us come back to this process here. John McGregor on his birthday party session said that young scientists should either solve new problems or solve old problems better. So I'm trying to solve an old problem better, because at Skogestad they have an RTO on this one. So they have put a lot of work in modeling it, estimating all the flows and all the parameters and data reconciliation. So I'm trying to do that in a simpler way that gives the same results. Okay, so if you write this down, you can write it like this, and that looks more like what I've shown you before. And here I've got some results. These ones are just the end temperatures of the different branches, and the network, this is the last row. That's what we're interested in maximizing. That's the important thing. So the first column is what we got, the data that we got from Statoil from their RTO. And that's what we use to fit our model to. So we use this data from Statoil, and they get this optimal point, which is 207. We fitted a MATLAB model to that and optimized that again. So this is the optimized MATLAB model, which is very similar. And then if we apply our approach, where we don't use any optimization at all, we just control the Jäschke temperatures in all branches to equal values, we get almost the same end temperature. But the difference is that we don't do any optimization. So here they did optimization, RTO in the real plant. This was with the MATLAB, with APMonitor.com, and this one here, we don't do optimization. We just control this temperature, the Jäschke temperatures to equal values, and we find a near optimal split. I'm not going to talk so much about this here, but this case is the same if you make flow disturbances or temperature disturbances. The values become very similar too. So this makes re-optimization unnecessary, basically. Okay, you want to see something too? Okay, and now an economic extension. Sometimes we want to use one heat exchanger more than the other, because, for example, we don't want to cool this second stream down so much, or because it's high pressure steam that we don't want to use as much, or for whatever reasons that you might internally have. So you can weight, you can make a cost function that you weight. So it's just like you sum up the heat that is transferred, and then you weight it with the corresponding prices. You want, so you want to minimize this cost. And in this case, it is very simple, because like the economic extension, if we just have two heat exchangers on then it becomes, you just weight the terms of the Jäschke temperature that I showed you before with these prices. If we have three, this looks like this. So you just have the same results that you had before. You just weight them with the prices. And obviously, if it doesn't matter which one you use for heating up, then you will just maximize the total heat transfer. So I got a simulation on that one too. Here's the cost that we want to minimize, and we have two prices. This means that we want to use heat exchanger 1 more than heat exchanger 2. So we have this control variable, and we see the operating costs are very similar again. while isothermal mixing, which actually doesn't make any sense in an economic context here, gives a lot more loss. So the lower this number is, the better. Yeah, the lower cost we have. Now you might say, okay, well, maybe this is very limited to some special topologies. Yes, it's limited. It cannot solve everything, but it might be more flexible than it appears on first sight. So if you have to take one of the degrees of freedom of such a system, for example, out to control something, then you can just use this valve here to, for example, or this flow to control some temperature or some constraint that you have on this branch, and for the rest of the system, the control structure remains unchanged. Or if you have a different flow structure, for example, that you have a hot stream coming in here and then some is branched off and then it goes back again, you can also handle this. The Jäschke temperature is exactly the same as we have here. Why? Because this here can basically be modeled as one heat exchanger by just manipulating the heat transfer coefficients and the flow rates. So any kind of structure that you can model as one or more heat exchangers on a row, then can be handled with this framework. That brings me to my conclusion. It's a very simple implementation. We don't need any online optimization and no flow measurements. So we can get the same result as the people at Statoil get with their online RTO. It is a lot simpler, so it's based on the arithmetic mean temperature difference, but it works very well also with the logarithmic mean temperature difference. And so you need to have some kind of common feed or some common constraint such that these optimality conditions can be written pairwise as the marginal cost. We can take prices into account, and we've also started a patent application. So if you have such a system in your plant, please talk to me after the presentation. I'd be happy to discuss it more with you, or send me a mail. And thank you for your attention.
Okay, great. Any questions?
So, your conclusions, do they apply to a heat exchanger network with only sensible heat, or both sensible heat and phase transition?
I don't have any phase transition.
Okay.
Yeah, I should have said that.
So it's limited to the only sensible heat exchangers. I'm not saying it's limited, but you guys haven't considered extending it to phase transition networks.
Yeah, so that's not there. We're not there yet now.
Did you consider the minimum temperature difference approach using the heat transfer coefficient?
Sorry, can you reformulate your question a bit? I'm not quite sure what you mean.
In practice, we have to consider minimum temperature difference for calculating heat exchanger efficiency.
Okay.
So
I think you have to do that, or usually, typically you do that when you design a heat exchanger. And when you design the heat exchanger, simple way or to balance cost and cost and efficiency is to do this minimum temperature. But what I'm considering here is you've designed a heat exchanger network for me, and you already did that. So, but I just use what I get. And actually, if you operate the system, then typically, or in most cases, you operate at a completely different point because these constraints of the minimum temperature differences are not active anymore. But so this here deals with operation of heat exchanger networks and not with design. You could probably also use it as kind of a shortcut method for designing networks like this, but or to add it as a constraint. But so I didn't do anything with the minimum temperature differences.
To implement this online, can you get away with just a simple ratio control type scheme in order to just balance out your temperatures for long-term support?
What are you thinking? Like,
well, I mean, a lot of what you were doing here was like a design methodology for how to balance it and compute where the appropriate point is. If you were to implement the scheme longer term, when you're going to have different fouling and different heat exchangers, so your temperatures are going to be changing over time. Well, how would you implement a control scheme then, basically, to account for that?
I would just make a. So you have a split. So if you assume that you have one valve on one side that you can manipulate, and that will then. So I just use a PI controller and control this here to 0.
What if you have a multiple? I mean, your initial example was like 10 different valves or something like that.
Okay, but then you just take the different, like, the first one minus the second one, the second minus the third minus the fourth, and if you make them all to 0, then they're all equal. Another approach you could then, so this would be one approach. Just make the first minus the second minus the third, and so on. That would be one approach. Another would be you make the first minus the average of all, the second minus the average of all, the third minus the average of all, because in the end the optimality condition says that the Jäschke temperatures on all branches must be equal. Did that answer your question?
Yes.
Okay, great. Well, let's thank the speaker one more time.